So we'll welcome those who are watching or with us virtually. And how many of you have watched the videos afterwards or haven't been here? Have you found them helpful? Okay, good. Good. So we'll keep doing them. Actually, I got to look at this. I think today's Tuesday. We'll do 13.1 and 13.2, which is going to deal with integrals from two different perspectives. And then on Thursday, I'm going to mix it up a little. I think we can do 13.3 and then 14.4. And that would really be the end. If we get the two sections done, that would be the end of the content portion of the class. Remember, I'm going to make 14.1 and 2. I'm going to make those extra credits. So you can still do them if you'd like, but we won't have any direct instruction. What that means is then the following week, next week, we will have 2 days that we don't really have to do any instruction, so they'll be more open-ended to, we could maybe do a test review if you wanted to. Basically, it'd be up to you if you wanted to come and had questions or something you wanted me to do. So it gives us like a week where we've got this overlap. After that, I'll be gone, so there'll be about that class meeting where basically you can review for the final, review for everything else, and then the final week I'll have a substitute here who can again answer any questions that you might have, so you'll have kind of a week on your own watching videos. Come back if you have questions, and then the opportunity to take the final in here on the final date, which is July 19, or as you've been doing, taking the tests with the lockdown browser. Okay. The other thing, again, I'd mentioned about if you got 90% on all three tests, you wouldn't have to take the final. I've thought of maybe adapting that a little bit because I have a few people who have requested to retake the first one. So what I thought is, what if you take each of the three tests, and the final is a retake of those three tests. But if you're satisfied with how you did, whatever that is, on the test, you don't have to retake that part, or you didn't have to retake any of it if you don't want to. But if you want to get a higher score, you retake whichever test you didn't do well on. Does that make sense? Okay, because that's really what the final was going to be anyway. Thank you. It was just going to be a series of the questions that we've already taken. So I think with this shortened version of the summer course, we'll just, if you do good the first time through, why do you have to do it again, right? At least that's what I think. So, let's see, who else needs a copy of the practice tests today?
I have a question.
Yes.
So is the final the third test or the fourth?
It would be a retake of the first, second, or third. So we'll have three tests.
Okay.
We've got Chapter 10 test that is done, and everyone's taken that. Some of you getting me your test corrections, and even if you only missed one, it pays to get me a test correction because you get at least half the points back. Again, the more explanation you get, the possibly more points you can get. There'll be a test on sections 11 and 12, this is what the practice test, and I took 2 questions out of each of the sections that we covered, and pretty much verbatim from the homework. So if you've done the homework, you have really seen all these questions, but this just helps you focus. This is all the types of questions you need to be able to do. Some of these are not in context. I didn't say use the product rule, but there's one that's set up that would probably be the easiest way to do it. It's not the only way. It doesn't say to use the chain rule, but you'll see that there's a couple that's what you would want to do. And if you I do have it in order from 11.1 to so forth, so you should probably be able to see, well, that was in the chain rule, that's probably what he wants us to do, or that's probably the easiest way to get that derivative. So that's what the practice test is for. I will do a written solutions guide like I did last time, and even on some of these, I think it might be helpful to have a video description, because then you can see exactly, because sometimes you take the derivative and yeah, you're just taking that exponent, multiplying and subtracting 1, but if I talk you through it it makes more sense. If you just see an answer written out, it might not be it. So I think on this, and especially because there was one, I think the chain rule, we didn't get a video recorded on that one. So I think to help out, I will do a video solutions guide as well. So whatever works best for you. And my goal is, things are happening faster and faster, but my goal is to have the test ready by maybe Thursday or Friday at the latest, so that as you wanted to, you could take it. This one I will leave open. How long should I leave? Well, I'll leave it open at least for probably a week and a half. But again, the sooner you take it, the better you'll know what you are, where you're at. And remember, the final exam will be basically in 3 pieces. There'll be 3 parts to the final exam, and you can choose to take one of it or none of it. If you do well on the first set through, they'll just be alternate tests from 1, 2, and 3. Okay.
So will the third exam be just integrals?
Yes, just integrals. It might be, and I'm going to work it out so that I've got to readjust the point values so that basically the homework and these 3 exams come to a total of 1,000 points. And if you get 900 or above, you've got an A in the class. If you didn't do well on one, and you want to, then basically the final, you could retake that portion. If you didn't do well on any of the 3, basically the final is an option to replace those scores. But everyone did reasonably well, so especially after the corrections. So I think you'll find you'll be just fine. Okay. So let's take, you ready? Okay, you guys are, I'm not quite ready yet. Is it okay if I take a break first? Oh, okay, well, good. Never had a teacher say that, right? Who was it? I think it was Andrew Dice Clay. Everyone see that? You know who he is? Comedian. He'd start his act off. He'd sit on his chair, like be having his coffee. He says, "Oh, when you guys go to work, you don't start working right away, do you?" So anyway, it's kind of a joke. I thought it was funny. Okay, so we'll start. Here we go. We've got a function. And this should be kind of review, but what I want to do is I want to get back to what we're going to do today by looking at where we've been. So if we've got a function, let's say it's 3x to the 5th minus 2x to the 3rd plus 4x minus 8. Okay. And I ask you, would you please give me the derivative of this function? Now, we'll go through and do it, but what are we getting when we get the derivative?
We're getting the function at that exact point. We're getting a slope, right? A rate of change.
Good. We're getting a rate of function, but we're getting a function that is a function of a rate of change. And so when we plug in a particular point, we get that slope, that rate of change at that point. So we've got I call it the mother function, whatever you want. It's the f of x is our mother function. The derivative is the function of how things are changing. So the mother function is what values we get. It might be profit, whatever. We'll just call it profit. So we plug it in, we get our profit. The derivative tells us how that profit is changing, and we call that the marginal profit. If we sell one more item, how does that change? That's what we're getting with the derivative. Okay, think of that. Okay, so let's now go ahead and do the derivative, and then we're going to talk about today's lesson. So let's change colors here. Let's go with sky blue. So when we take, and I want to go a little bit more step by step with it. What do we do when we take the derivative of the first term? We take the exponent here and we multiply it times the front number. Okay, so that gave us 15. Then what did we do? Subtract 1 from the exponent. So that gave us 4. We come to the next term, and this is a sum rule that we could do it term by term, which was really cool. Because we saw when we had a product, we had this funky stuff we had to do, but when we just had things added or subtracted, it really wasn't too bad. What do we do with this one? Take the exponent, multiply, I guess I should say multiply, right? 2 times 3, or actually negative 2 times 3, we'd get a negative 6. And then what would we do to the exponent? Subtract 1. Gets kind of boring, didn't it? Multiply and subtract 1, if that's pretty much what we were doing all along. This one, what's the exponent we got here? 1. So there's an invisible 1 exponent. Again, we take it, multiply, and then we subtract 1. So 1 minus 1 is 0. X to the 0 power is 1. Anything to the 0 power is 1, so we didn't write it. And then what happened when we came to this, what did we call the last term? That's a good word. Constant term. We take its derivative, and the derivative of a constant is always 0. Because remember, it's like the last part's like a horizontal line. Its slope is 0. So plus 0 at the end, but we don't put that. Okay, so, but this is pretty important that the constant in effect disappears from the derivative function. You don't know that there was a negative 8 there because it's just completely gone. You could see the 4, you said, oh, there must have been a 4x. You could see the 6x squared, and knowing this is a derivative function, you could think, well, if I went backwards, there must have been like an x to the 3rd in that place, and we'll figure out. So, and that's exactly what we're going to ask you to do today. What we're going to do today, so this was take a function, take its derivative. What we're going to do today is we're going to start with the derivative function, and we're going to go backwards, and we're going to call that integration. Okay, so let's just think of what we did. What are we going to do with the exponents? To take a derivative, we subtracted 1. So to integrate, we are going to add 1. Makes it, because we're going backwards. That's all we're doing today. So if you've done well in the previous stuff, this stuff should be almost basically the same thing, but in the reverse order. So on the exponents, we're going to be adding 1 to get back to what we started with. But the thing is with this function, if we started with it, how do we get back to this 3? How do we turn this 15 back into 3? Good. You add first and then you divide. Remember, when we were taking the derivative, so this is where it's all backwards, the derivative we multiplied first and then subtracted the exponent. When we take the integral, we're going to add the exponent, we're going to add the 1 first, get the new number, and then we divide by that exponent. Exactly. And that was the hardest problem I had with this, is I didn't do it in the right order. I would oftentimes divide first and then add, and that messes everything up. So let me just give you an inkling of what our problems are going to look like. A lot of times they'll just give us this, but what we will start with here is we're going to integrate, and they give this sort of a symbol for integration. They give us the derivative function, and then we've got this dx here to remind us that this function is a derivative. Okay, so what we have is a derivative. That integral sign looks like a funky S, and it's sort of an S because it's the way they did this is by sums. We'll do that in the next lesson, that sort of go back to the old school way of they get these, but they summed up. Basically, they end up getting the area under the curve. Okay, so we're going to be able to do this, but before we do this, let's think about this. What is a derivative? Again, we just talked about it, so what is a derivative? A rate of change. So if we go back from a rate of change, what are we getting?
just a function?
We're getting a function values, and what we're going to see is that we're actually summing them. We're getting, when we go back this way,
You just get a point.
actually we get an area. We get an area under the curve. This is a way, it's an accumulation. So if you know the rate, like I'm standing at a concert and I know that there's 10 people per minute coming through the door. If I know that, I can take a sum after 10 minutes, how many people have accumulated in that concert. So this is where this is the application, is whenever we're getting an integral, it's an accumulation of stuff. Okay, so by knowing the rate, what we do is we measure how long was that going on from the start to the finish. We get how much has been accumulated. So like at an oil spill, if I know how fast the oil's coming out, and I've got some sort of a function, because usually oil spills are circular, so that would be my function, is I use a circular function. I can say, well, it's been spilling for 2 hours, so from 0 to 2 hours, how much oil have I accumulated in this bay? How big is my problem? If I don't get it solved now, how much more are we going to get? So this is the accumulation. So this is the mathematical accumulation. Yes.
So, would it be like, would a good example be if you have like a pressure volume curve, and the area under it would be like the total work done by the system?
Exactly. Yes. So yes, we're not even just getting values, although we get to a function that looks a lot like the original function. But you're right, what we're thinking of, we're starting with a rate, we're accumulating it, and we're getting accumulation of stuff. Yes.
I was doing that homework, and I think they were doing this integral stuff, but they just like started you off with a derivative function,
Mm-hmm.
and then they asked you later on like what the function, like the cost function or the marginal function was, like before the derivative. And is that like, do you need to use the integral function if they only give you the derivative and then you're just trying to find like the regular marginal or cost function if they don't give it to you?
Right. You could use it, if they gave you the marginal, it's how we could use the integral to get back to the original cost function.
Because they don't give you it originally.
Right. We're going to see we get close. We're going to see that we can't be completely certain, because remember what became 0 when we took the derivative? The constant. We don't know if that, when we go backwards, that's been lost because it became 0. So there's sometimes, there's part of this where we get close but we're not exact. Okay, so we'll focus on the process of getting the integral, because that's pretty much what the homework is. They give you a bunch of problems, ask you to get the integral. There's a few questions at the bottom, but just basically think whenever we're getting an integral, we're getting an accumulation. Whenever we've got a derivative, that's a rate of change. So these are the two things of calculus. Accumulation of work, accumulation of whatever. So the way we go about doing this, let's go with red. So the first thing when I integrate, I'm going to add 1 to the exponent first and get my new exponent. So I'm going to have x to the 5th. And then now that I've got my new exponent, I'm going to take whatever was there and divide it by that exponent, right? Because that's how I got that 15, is that exponent came down and multiplied first. So I got this thing, I'm just going backwards. I've tried to undo this function. And so 15 divided by 5 is 3. And notice that matches up with what we started with up here. Okay. Although, again, when you do the problems, they don't give you the original function. That would be too easy. But that's what we're trying to get. Okay, and then I go to the next one. Again, I have to remember to add the exponent first. Add 1 to the exponent. So 2 plus 1 is going to give us x to the 3rd. And then this 3rd is what I would have multiplied by, right? So I come up here and I divide it by 3. So I get my exponent first and then do the division. Same thing we were doing, but in reverse order. So negative 6 divided by 3, I think that gives us negative 2. And if we look up at the very beginning, yes, we had negative 2x to the third, negative 2x to the third. So we're just restoring back to what was originally there. Okay. This next one's a little maybe weird, but what you have, what's 4, what would be the variable down here? X to what power? Right? That last one, that constant, was really an x to the 1. We subtracted 1, we got x to the 0, so we didn't write anything. So this last one, we want to think of it as x to the 0. So now we have something to add 1 to. So 0 plus 1, this is x to the 1 power. And a lot of times we don't write that 1. So I take this exponent, I take the 4 divided by 1. Okay. And you might just come to the end and say, well, that's 4, it should be 4x. Okay. But that never made sense to me because I integrate by adding 1 to the exponent and dividing. This makes sense to me. Okay. What's missing from my integrated equation?
Constant.
The constant. So what should I put there? How about plus a c? And you'll see in the answers they've got that, at least I looked, the ones I looked over, they've got a place to put the new function and then they put plus c. When I took this stuff, if you didn't put the plus c, you lost a point. I lost lots of points because I'd always forget the plus c. But this homework, they got it for you, so you're never going to have to worry about forgetting it. It'll be there. You'll see it. I think it's always there. At least it's there a lot. Okay. Questions?
How do you find C?
You can't. It's been lost. Sometimes when you delete something, you never get it back. Well, you need some more information, and that you need like an initial value and a possible value. Then you plug those in. It's a bit of work though to actually figure out what that is. But you need some particular data values, so it can be gotten back. We're also going to look at one where we get to a definite integral. And we don't even work with the c because we've got a starting point and an ending point. We plug those values in and we get the values we need. Okay. So does this look okay? Can you think of maybe where there is, you think there might be any place where this might get a little tricky?
Square roots and fractions.
Okay. Square roots and fractions. That's exactly right. So we're going to get a clear page. Let's change our color and let's take a look. And again, this time I'm going to start with the derivative function. So we'll just write it with this little integral. And what they do is they put the bottom, they put limits on the bottom and the top. So those are, they want you to go from an x value to another x value. So we'll see that in the next section. But for this first section, all they want us to do is integrate. So yeah, let's go with 2x squared minus 3 over x plus, and let's throw it all together, plus the square root of x dx. That looks a little more challenging, right? So when we took these derivatives of functions like this, what did we do first? What was our action? Did what? Make it so they're not fractions. So we use negative exponents, or even the square roots, we would write that as a 0.5 exponent or 1/2. So we made everything so there was an exponent because we knew we were going to have to subtract 1. This one we're going to add 1, but we want to have the right thing because you can see if you take 2 over x squared and you add 1 to it, you might think you got x to the third, but we're going to make it a negative exponent. We see we don't get x to the third, we get something else. But we want to work with the exponents in the right place. So the first thing is yeah, let's just rewrite this as the integral of, move the x squared to the top, and that makes it become x to the minus 2. Okay, so we can see we're still going to add 1, just like we did last time, but we get something different. So except, how should we handle this one? Well, let's just do it. And I'll just let you know in advance, this is going to be the tricky one, and you'll see why. And then we could write this as x to the 1/2, or if you like decimals, 0.5. Okay. And then they still have this dx. It's not real important, but it's still the derivative function, and we want to go backwards. Okay, so let's go ahead and start out here. So with the first term, what do we want to do to integrate? First step is to plus 1. Exactly. It's the simple things. We're just adding 1. We do that first, so that's going to give us x. -2 plus 1 is -1. What we need to do with that -1 is we need to take the 2 divided by the -1, just like we did on that last problem. Figure out what the exponent is, and then divide the coefficient, the number in front, by the new exponent. Okay, so it's just same thing, but just a little scarier because it's negative exponents and it just doesn't feel as natural. So we take 2 divided by -1, giving us -2. What do we do here? Just add 1. -1 plus 1. Ooh, x to the 0. So then that means we take the new exponent, so we take -3 and divide it by 0, right? And that's what we've been doing. But does that cause some problems? You betcha it does. It gives us something that's undefined. And this is, I wasn't quite sure how to teach this, but this is a problem. This isn't going to work. This is the one place it just doesn't work. But if you remember what we did last Thursday, I think it was last Thursday, when we ended up with, say, 1 over x as the answer to a derivative, where did that come from? What were we taking the derivative of to get 1 over x? You remember? It was one of those funky equation, funky functions. Something we don't use a lot. Something that I said you'd probably use if you were into economics or finance. It involved the natural numbers, or a natural number. It involves e, but not the exponential e. What was the other? Log of e, natural log. When we had the natural log, which we wrote as natural log ln of x, when we take this derivative, we get 1 over x. So whenever we have 1 over x and we want to integrate, this is the one we cannot use exponent things. We cannot add 1 to the exponent. We have to remember that it's going to give us a logarithm. This was the hardest one for me to do because you just want to get in that pattern. This is the one that's a special case. Okay, so I'm going to drop down a line and say, oops, problem here. So that didn't work. What we're going to do is we're just going to go down here. We're going to come back here and say, well, what's 3 over x? That must have been, I must have had the natural log of, I must have had 3 times the natural log of x, right? Because it's just what's in the bottom was in here. It may be -3. If I take the derivative of this, this is a constant multiplier. That just goes there. And the derivative of the natural log of x is 1 over x. giving us negative 3 over x. That's what we started with. So when we go backwards, what we started with is negative 3 natural log of x. Okay, that's going to be the tricky one. But it only occurs when we have a singular x, an x to the first power in the denominator. So watch for that. And you'll kind of catch it, because if you turn it to a negative exponent, you'll get x to the 0, which makes it disappear. And you'll end up dividing by 0, which is a no-no. And so you say, wait, that doesn't work. So everything else is okay. This 0.5 exponent, what do we do with it? Add 1, and we're going to be okay. So this is where that was the only problem we're really going to have. Add 1 to the exponent. Do that first. So now we're going to get plus x to the 1.5. And then what do I have to do with that new exponent, the 1.5? I need to take the coefficient, which was actually a 1, and divide it by 1.5. So this gives me x to the 1.5 divided by 1.5. You could write it that way. You could write it as a little fraction. But let's just kind of double check. If I were to take the derivative of this, okay, so this is our answer here. Oh wait, almost our answer. What did I forget? Plus c. Yeah, so typical form, I forgot the plus c. But again, your homework will give that to you. Because there could have been some constant there that when they took the derivative it became 0, so it disappeared. And we had no other way of finding it out. Okay. One way, the nice thing about this is we can always check our answers by doing what? Take the derivative, right? So take our answer and make a derivative of it and see if it's what we got back to. This is equivalent to, in algebra, of factoring. We could multiply out, or we could factor. Oftentimes we would factor and then multiply back out to see if we got what we started with. So as a check, take the derivative. Derivative. Okay. So let's go step by step. We got negative 2x to the negative 1. If we take the derivative, what do? We take the exponent times the coefficient. So negative 1 times 2. We do that one first. So that's going to give us a positive 2. And then what do we do to the exponent? Subtract 1. So this is, yeah, it's kind of hard. You're going to be going backwards and forwards, but it's actually good practice. So we subtract 1. Negative 1 minus 1 is negative 2. Okay. Here we're going to take the derivative of this. We don't need to use the product rule because it's a constant multiplier, but we'll get the derivative of natural log of x is 1 over x, and then we've got the constant multiplier out front, minus 3. So yes, it's going to be negative 3 over x, okay, which is what we started with, so that's looking good. If we take the derivative of this next one, what do we do first? Before we subtract 1, multiply by the exponent, right? So we're going to take this 1.5 and multiply. 1 times 1.5 is 1.5. So there's a 1.5 here. What's 1.5 divided by 1.5? 1. So what we get is we get a plus 1. Then we subtract the 1. So this is, subtract 1, we're going to get x to the 0.5. Okay, and that's what we have. We have 1 square root of x, which is x to the 0.5. Okay. So we don't have to formulate. This is not our answer. This is a check of our answer that, hey, we rock. We did it. work. And then if you wanted to, the derivative of the constant is going to be 0, so that doesn't show up. Okay, so that's what's kind of nice in learning this, is we now have a means to check our answers, whereas before we really didn't. We had to kind of just do it. But now we can integrate back to the original one. If we take its derivative, we should get back to what we started with in the question. Okay. So we're feeling pretty confident here. There's our answer. Anything else that you can think of that might be a difficulty?
Are we supposed to put an absolute value in the natural log? It's one of the homeworks.
Yeah, that's what they usually, because you can only put positive values into a natural log. And again, that's all another area I always got marked down on is, yeah, it's a technicality. But it's probably an important technicality. So yes, with natural logs, we should have that absolute value there so that we're making sure that we have positive values going in. Because x could be negative, and that's one way to sort of solve it. So yeah, so if your answers involve a natural log, probably try to use those absolute values. It might mark it wrong. It might let it go. I'm not sure. Sometimes the WebAssign is a little different. Okay. So why don't we do this? Why don't we take a look at the homework, see if they gave us something that's anything different than we looked at. I don't think so. I looked at it earlier, but I might have. Sometimes I don't. I miss something, and I think, oh, that should be easy. And you'll look at it and say, no, it's not. Okay, so let's pull up WebAssign. Come on. Here we go. Because we're here. So you found one already, huh? Okay. You got it. That sounds like about the area where we get some funky stuff. So I'll go in student view, and then we'll go 13. Wow, we're a lot further than the indefinite integral. And then we'll look at something, actually not 13.2, we'd look at 13.3. So again, just kind of what we're doing, not too bad, right? Remember, add 1 to the exponent and then divide by that exponent. So let's take a pop down at what we got going on with 11. Ooh, yeah, it looks like it could be, but looks like the hard part of 11. Fractions. What about those parentheses? Does that throw anyone off? Do we need those parentheses there? Not sure, huh?
What's a du?
It's dx, but since they're using u, is, yeah. So think you could do this whole with x's, but since they're using, it's just a derivative with respect to u. So they're just using a different variable. So there's another thing, is it looks maybe confusing because they've got this u, which we usually use for special substitution cases, but we could have used x, but they're using u. The parentheses is just kind of to group it. It's really not needed. So we could just think of this as we're being asked to integrate this u in the fraction. That's that looks kind of, so what should we do with this first term here, 9 over u squared?
Turn it into -18.
close. Yeah, just because whatever's in the bottom, move it to the top, so the 9 stays a 9. But, yeah, if we were going to take a derivative, it would become 18. But we're going to see we're not taking derivatives, right, because we're dividing. So we got to get our orders straight here. How about the second one? Is it okay? Could we write it as not a fraction? How about, it probably could be done either way. We could write it as 1/2 u to the third. Okay. Or you could u to the third over 2, whichever way you want to work with it. That's fine. Okay, so now our process, we've got the 2 terms. That's all it is. Oh, there's a du at the end, right? And see, this is what I mean. They put the plus c there for you, so you don't have to worry about this. So what's our process? What do we do first when we take an integral? We add 1 to the exponent first. Thank you. I was forgetting myself. I got myself so mixed up. When you go back between derivatives and integrals, it's easy to mix them up. But this one, we want to add. In fact, maybe we put a note over here. Steps. So 1, add 1 to the exponent. Step 2, divide by the new exponent. And that's really all there is, step by step. Add 1 and then divide by the new exponent. So we come here, let's switch colors so we can kind of see what we're doing. So we're going to add 1 to this exponent, so -2 plus 1 is going to give us u to what power? -1, exactly. Then what do we do with that? Yeah. Sometimes you get yourself thinking you're smarter than you are. That's what I do all the time. And because I thought that 9 was going to get divided by 3, but I was trying to do the math in my head. Yeah, so I was wrong. So that's why you have to do these step by step, because you know, how many of you else saw that 9 and saw the 2 and thought, oh, we'll just divide by 3? Or yeah. We don't do that though, right? So what do we divide 9 by? The -1, the new exponent. Good. So this gets divided by 1. So our new coefficient is -9, u to the -1. Good. Next stage, we come to the next term. What do we do to this 3 exponent? We add 1. Remember the first day of class? How many of you remember that first day? What did I ask you if you were able to do? Add and subtract 1. Isn't that really all we've done this class, is add and subtract 1? Pretty much. That's all calculus is, adding and subtracting 1. So now we're getting into the add 1 time. So 3 plus 1 is 4. What do I do with that 4? I take 1/2 divided by 4. Now this is where it's maybe a little tricky. But if I take 1/2 divided by 4, what ends up happening? I think we end up with 1/8. So what you get is you get 1/2 divided by 4, which is 4/1. Think of it, right? And when we divide fractions, what do we do to the second fraction? We flip it. So this is equivalent to saying we had 1/2 times 1/4. And this is why this was maybe one of the more challenging ones. 2 times 4, what we're going to end up with is 1/8. Okay, so we get plus 1/8, oops, not 1/2. 1/8 u to the 4th. And let me just put that in there. oops, wrong keyboard, negative 9 u to the negative 1 plus 1 divided by 8 u to the 4th. Look good? I think they should accept it. Again, if you wanted to go through this to check your answers, take the derivative, you should get back to what you started with. And I can kind of see here, if the 4 comes down, 4 divided by 8 is going to be 1/2. 4 minus 1 is 3, so that's good. This one, a negative 1 times negative 9 is going to give us a positive 9. Subtract 1, we get a negative 2, which is give us that. So I think we're good. Okay, so working backwards and forwards, and we got the green check mark, so we're in good shape. Did that match up? Did that help? Was that exactly, did you guys get the same answers when you got different numbers in there? Okay, but the template's about the same, right? Okay, so good. So that's all we're doing today. We're going backwards from what we've already learned. No funky, we don't have to use a chain rule here, because the ones I kind of put out, there's stuff like called integration by parts. There are some techniques that I'm purposely, you could, if you want to, they're there, but they have very specialized applications. And that's why I said, why should I have everybody do something 99% of you won't ever use? Okay. If you're a math major, they make sense because they connect with mathematics, but for most of you, you're doing an applied program in business or economics or something that doesn't really need to know all that stuff. This is good enough. Adding, subtracting. So we're not going to get into the place where we have to do the equivalent of the chain rule, the product rule, or the quotient rule. These are all going to be pretty straightforward. It's just add 1 to the exponent, divide by that exponent. Okay. Beautiful. And let me save this page. There we go. You'll see we only have a few more problems here, and they get a little funky with some now this 1 over x. Do you remember what's going to happen with that 1 over x? What is that going to integrate? Natural log. You just have to remember it is the natural log. This is the one we don't add 1 to the exponent because it's a weird one. Whatever you want to think about it. It's different. Let's put it that way. Weird is kind of like judgmental. It's different. It's special. Sure. So when we get doing these, what you're going to see is it's the most helpful thing to do is when you see 1 over the x, don't rewrite it with a negative exponent because that's going to lead you to want to add 1 to that exponent. So, 1 over the x, that's that special, that's that one that thinks it's so special. It is. So we're going to leave it as 1 over x. And then what I will do with these other ones, though, they are not special. We're just going to rewrite them as negative exponents. So I would rewrite that as plus 4x to the minus 2 minus x to the minus 3. So far, so good. When I integrate these, I just remember, that 1 over x guy, that's that special case. That's just natural log of x. Natural log of x. And to make our software happy, we put in absolute values. Maybe we don't have to, but we'll. And this will be good because then we'll look at how to. Does anyone know how to put absolute values in here? I think there's a place to choose them, but I haven't actually done it, so we'll learn together. What do I do with the next term? Add 1 first. So negative 2 plus 1 is going to give us x to the minus 1. And then what do I do? Divide by the new exponent. Negative 1 there. 4 divided by negative 1 is just negative 4. Good. Come to the next one, negative 3, add 1 to the exponent. Negative 3 plus 1 is negative 2. and then I have to divide by the new exponent. So this was a 1. So negative 1 divided by negative 2 is going to give us a plus 1/2. So there's our answer. I'm going to write it over here and then put it in so to do a double check. So natural log of x, I'm going to rewrite this as minus 4 over x, moving the negative exponent down, and then I'm going to write this as plus 1 over 2x squared. Now you could probably write it with the negative exponents, whichever you want, but this is my personal preference, because we were supposed to write everything with positive exponents when I was doing this sort of stuff. And let's see. So natural log, let's just put in the x and see if that's okay with the system. And then we got what? Minus 4 divided by x plus 1 divided by 2x squared. Does that look good? Did I miss anything? We'll see if it needs the absolute values or not. Just that's what if it does, we'll go figure out where they're at. I think they're somewhere in there. Yeah, I didn't like it. Let's see. Did I mess up anywhere? Where did I mess up?
Isn't it plus 4 over x minus 1 over 2x squared?
Plus 4 over. Well, remember here, this was 4x to the minus 2. I have to divide by the new exponent, so 4 divided by negative 1 should give me a negative 4. And this, I think it's the absolute value. The absolute. So what we have to do is come back here. We have to figure out how to put absolute values in. See what, there's no markers here. It's functions. So if I click on functions, oh, there it is. Oops, but I have to put the x inside. So come in. Yeah, I think that's the only problem. Let's.
Then you have 1/2 x to the -2.
Yes. So 1/2 x to the, you can put it in this way if you want, but or you could put it also as 1 over 2 x to the positive 2. So these two are equivalent, right?
That was 1 over x cubed.
It was, but remember we're integrating, so we had the x to the -3. When you add 1, that gets you to the -2. Yeah. So I mean, this stuff is simple, but it is confusing because it's a simple thing. We're adding 1 instead of subtracting 1, but I tell you what, that's sometimes the hardest thing to do is to do something that's sometimes the complicated things are a lot easier to do because they're so straightforward. There's one way to do it. But this is, your brain has gotten used to subtracting ones and dividing, and you'll get where you're just looking, heck, I don't know which way is up anymore. So that's, you know, I mean, when I say this is simple, I mean it is, but mentally, these are difficult tasks that you're asking your mind to do. Backwards and forwards, those are actually fairly difficult tasks, and that's why you need to train. That's why, you know, athletes do things all the time, but in their practicing, they make the difficult things, the strange things, normal for them. It's not normal to throw your head at a ball, but people do it.
I mean, if you divide by -2, wouldn't you be getting a -1 over 2?
You would, but notice we divided by -2. We had a -1, so we had a -1 divided by -2. Yeah, so and there's all these details in here. So I'm glad you asked about this, because whenever we have a natural log, we have to make sure to put those absolute values in. Thanks, bud. That's good. Okay. So that's the trickiest of them all, pretty much. Oops, let me save this as a picture. If I do that, the note should have everything in. And again, just make these into negative exponents, add 1 to them, divide by them. You'll get through. So just that process. Add 1 to the exponent, divide by the new exponent. Just keep doing it. The only place we don't is if we have a 1 over x. Then that's the natural log. But everything else that's all it is. That's all it is. Okay, good. Oh, we haven't, I guess I didn't talk about e to the, I didn't think we'd have one. So should we talk about this one? Because again, it's the easiest one, but it's also the one that you'll get to and you say, well, what do I do with this? So e to the x, what is the derivative of e to the x? So if I have e to the x and I have to take its derivative, what do I end up with? Sort of e to the x. I end up with what I started with. E to the x is like this really cool function. It's its own derivative. So the function values are also the rate of change of, it's just its own. It's weird, again, but this is the one thing that it's very special. Just like the natural logarithm has a special derivative, e to the x also does. Again, it makes it sort of simple, but it also makes it something different. So one more thing to review.
I mean, wouldn't it technically be e to the x times 1?
Yes, yes. Because using the chain rule, the derivative of x is 1, so yes. And that's where we're going to use, I think will be okay with a constant. We're not going to get any funky stuff going on. Okay, so do you want to see this whole thing? It's up to you. Or do you want to just see the e to the x? I was afraid of that. It looks hard, right? Okay, but we'll deal with it. Okay, 6.9. I'm going to rewrite this as 6.9, and what am I going to do with this in the basement? Move it up and rewrite it as negative 0.5. Plus, that's fine. Now this 6 I can't move up, so I could rewrite it as 1/6. Maybe that's easier to deal with, I don't know. X to the 0.5. And then I've got my minus 7 e to the x. So let's do this first one first. What do I do to the exponent? Add 1. So negative 0.5 plus 1 should give us a positive 0.5. And then what do I do with my new exponent? Divide by that new exponent. So 6.9 divided by 0.5 should be 3.45. Is that 3.45? Okay, good. Not so bad so far. What do I do here? Add 1. Nice thing here. 0.5 plus 1 gives us x to the 1.5. What do I do with that exponent? Divide by the 1.5. And you'll see that basically when you divide a fraction, the 1.5 will multiply by the denominator, right? Do over here. 1/6 divided by 1.5 over 1. Flip the fraction. That's 1/6 times 1 over 1.5. So that should give us 6. That should give us 9. 1.5 times 6 is 9.
Wait, isn't 6.9 divided by 0.5
see, that's when you try to do things just in your head. I was dividing it in half, but I should have, yeah, okay, I was dividing by 2. Thank you. I'm glad you didn't let me go all the way to the end with the, good. So it's, yeah, because when you divide by a decimal, you should get bigger. I should have caught that. Thank you. So we're going to, what was, it's 13.8. And again, when you're doing these, this is a good thing to use the calculator because you're doing things backwards and it's easy to get mixed up. See, what was this? This was positive, and this is going to be 1 over 9, 1/9. Okay, and the last part, e to the x, when I integrate it, I just get itself, e to the x. And if I took its derivative, I get itself and whatever it's multiplied by when it's multiplied by a constant. So constant multiplier doesn't change. Don't have to worry about chain rule or product rule things. Okay, so it ends out, it's kind of weird, and then again plus a constant, but they get the plus constant there. Okay, how's that? Yes, sir.
Why doesn't the negative 7 e to the x change?
They do a theorem, or basically when you have a constant times a function, when you take its derivative, that constant stays the same. So if we were to take the derivative of negative 7 e to the x, we take the derivative of the function and just keep the constant multiplier. That's its derivative. What might make it a little clearer if we thought about it in terms of the product rule. So I think I have enough room here. Let me change colors though. Actually, let me take a picture of this. Put the screen down. So let's look at this negative 7 e to the x. So let's look at this as negative 7 times e to the x. Remember, if we look at this as two functions, say g times h, to take this derivative, we take the derivative of the first function times the second function unchanged plus the derivative of the first function unchanged times the derivative of the second function, right? So let's do that. So what's the derivative of negative 7? 0 times e to the x plus the first function unchanged, which is negative 7, times the derivative of the second part, which is e to the x. Notice this first part is just 0. So our answer is so the negative 7, I have no, I mean, it sort of explains it, but it's just it's like a parasite. It just tags on for the ride. It's when we've got a constant, that's the nice thing we can do. When we take a derivative, it's going to be there. When we integrate, that constant's just going to come along for the ride. And because the e to the x doesn't have that rule of we're adding 1 to the exponent and then dividing, it doesn't get divided out either. So it's just that e to the x is such a clean function to work with when we're with calculus. It's its own derivative, it's its own integral, it's like the super identity when we're talking about functions. And there's nothing else like it. It's the only one. It's very unique. And so yes, it doesn't follow the rules. And that's what makes it hard to work with. You go, really? This is all it is? Yeah, it's all it is. And that's the hardest part. Does that help?
Yep.
Kind of. I know, I never felt it help. So that wasn't a good explanation. It just is because it is. Okay. But that's sort of how it is. Okay. Now, I'll be honest with you. This next section, we okay so far? I mean, that's so this whole section, 11.1, add 1 to the exponent, divide by the new exponent. You're pretty much set. With the 2 special cases, 1 over x is going to integrate to natural log, and e to the x is going to integrate to itself, e to the x. They sprinkle a few of those in there. Everything else, just change them to exponents, add 1 to the exponent and divide by it, and then it's just watch your math. The arithmetic part of it. It's going to be easy to mess up. But that's where you get 3 chances. So when it's got a wrong, check those things. You're probably doing most of it right. You probably did what I did. You divided when you should have multiplied, or multiplied when you should have divided, or something. But you'll probably be okay most of the parts. Now let's just jump in to look at a few of the examples from the next section. And I'll give you, there's a few word problems, but again, what they're giving you is the rate of change. You're getting back to the cost function. So they're giving you a marginal. The way to get back, the function from a marginal is to integrate. So that's the story for all of this. Even when they give you word problems, you're given a derivative function. Go back and find the original. And remember, basically, we'll have a full lecture on Thursday, but we have all next week. Both Tuesday and Thursday are going to be open days, open lab. Any questions you have, we'll sit, we'll work through problems. A live stream if you want. If you're not able to get to class, or you're used to watching the live streams, if you want to email me with some questions you want to go over, that'd be great. And by then I will have the 3rd practice test as well, which will be a little bit shorter because it's really only going to be 4 sections. Okay, so, and this is one of them. Probably most of the problems will come out of this section. Let's see. Let's go back here. Let's go to 13.3. So this is what we're going to call the definite integral. And what a definite integral is that's sort of, we don't have to worry about that constant because we're going to be given some boundaries, limits on it. Okay. And I was working on this at the beginning of class. There is a really cool program that I think I got downloaded to my computer, but I couldn't get it downloaded to my calculator because the connection wasn't working. But I'll show you. I think it might still be here. Curvature 8xp. This is a calculator file. I've got it downloaded. What I'll do is I'll put it into Canvas. What it does is it automates all this whole process that I'm going to show you now, and it does it graphically. If I had it, I'd download it to your calculators. But if you want to stick around, we could try, maybe with the Windows program, sometimes it works better. I've got a Mac, and sometimes they don't talk well with the calculators. But if I can download this program, it will actually do this whole program, solve this problem for you, and it will show you the graph of what's going on. I'm going to sort of draw it by hand, and we'll do a little bit walking through with the calculator on sort of manual mode. But there is that program that just, you plug in the function, you plug in the constraints, and it does it for you. Okay. So this is the way they actually, in the old days, much older than I am, hundreds of years ago, and this is what they still make students do. They do something called Riemann sums. Okay, and you're kind of going to see what that means. What does the word sum mean?
It's a total of 2 things.
Yeah, add, total. We're going to add something. Riemann is just a guy's name who did it, so they put his name on it. Okay, so, but what it is it's going, notice what we're finding is area under the curve. So what they did is they took this integral, and we're going to find, there's other methods to do this. So, and they're going to give us a boundary to do it on, and then what they're going to do is they're going to tell us how many rectangles. This is a method of using rectangles. How many rectangles we're going to use to calculate. Okay, and the thing is these are very rough estimates. The more rectangles we use, we get smaller and smaller areas, the more accurate we get. So I'm going to give you, let's just say, well actually this is probably not too bad, but what we're doing in theory in this problem is x is going from 0, here's 1, here's 2. We're going to make 4 rectangles, so that means we're going to have a rectangle that is at a half, at 1, at 1.5, and at 2. Okay, so those are going to be our rectangles. There's actually 3 kinds. There's a left Riemann sum, there's a right Riemann sum, and there's a center Riemann sum. What that means, what they're talking about a left sum, and again, I could use this one, but let's see. I don't want to. So if we had a function, so this is just a general, it said looks something like that. What we're doing with a left Riemann sum is we're going to let this function value, when x equals 0, be the top of our rectangle. We draw over here and we go down. So what's the area of this rectangle? It's 0.5 times what this is. And what is the height of this rectangle? F of 0. Okay, that will give us the area of this rectangle, and notice it's not, we're missing some parts of the area under the curve. Okay, to draw the next rectangle, we come to 0.5 and we get its function value, so it gets us a new rectangle that goes to the next boundary. And notice that's a pretty good one. Again, it's got a 0.5 is its base, and the height of this is f of 0.5. Okay, so this is going to be tedious to do by hand, but we will handle it. At 1, what we do is we go ahead and get the height. We go all the way to the function value here. We go over to there. Notice we've overestimated here. But again, the base is 0.5 times the height of this, which is f of 1. And finally, we do this last one, where we draw this rectangle. We go to the function value, cut over to 2. And again, the base is 0.5, and the height of the function is f of 1.5. So we figure out what these function values are. So we look up on a table of values, and we'll do that for this other one. We add up, and we multiply it all by 0.5, and that'll give us an estimate of the area under the curve. Okay. Does that make any sense? Sort of. Draw boxes, the rectangle, area of a rectangle, base times height. That's all we're doing. It's just the height of the rectangle is the function value at, in this case, the left point. If you do a right one, you do the same thing, but you're using the right values. So we would have started, instead of starting with f of 0, we would have started with f of 0.5, and we do the right sides. If you do the one that says find the Riemann sums of the center points, you go and the center point becomes that function value. They also have ways called trapezoidal. That's a little bit better. They've got a couple different ways to do this, but I think this is really, we're either going to do a left or a right Riemann sum. And the like I said, I wish I had that. I think the program I've got is the one that I've used it before. It's just really cool because it'll draw the graph. It draws in all the rectangles. It gives you the answer, and so you don't have to do all the tedious parts.
Do we have to add all the rectangles?
Yes. So we'll do a few of these. There's 5 of them. You tell me when you want to stop. I mean, you guys are paying my salary, right? So it's like kind of more like I work for you than anything else. So you tell me, that's what I got to do. Yeah, let's just do them all. Again, you'll also have slightly different numbers, but you'll see the process. And I think if we work a few of them, we'll be fine. But there's only 5 of them, so we may end up doing them all, which is fine with me. They're actually not too bad. They're just tedious. But let me just take a quick overview. Okay, not too bad, not too bad. Original marginal cost. Use minimum sums with n equal to 5 to estimate the cost. This one might be a little painful, so we'll do it. And then 5, we're given this. Minimum sums with n equal 5. So minimum sum with n equal 5 to estimate total U.S. population. Okay. Yeah, we got time.
So we're literally just finding the area of rectangles.
Yes.
There's no like short way to do it. You have to do each one.
Yeah. Well, if you want to match their answer, I'll show you when I do this. There's a real quick way to actually get an exact answer because your calculators will do this. So I'm going to show you both, but it won't work when they're wanting Riemann sums. So, but I'll show you how we walk through this. Okay, so first of all, we've got a function, 128x minus 32. Does anyone know what kind of function that is? What do we call that? Linear. So it's going to be a straight line. It's going to be going down. No, it's going to be starting at negative 32, going up by 128. We're going to do it from 0 to 2, n equals 4. Okay. So what we're going to do is we're going to graph this, and the things we are going to need are, we're going to need the function value, since it's what's left Riemann sums. We're going to want the function value at 0, 1/2, 1, 1.5. So we need 4 function values. Okay, kind of based on that picture that I set up. We're going to multiply them all by what the base is. So 2 divided by 4 is 1/2. So that's how you get what you're multiplying by. And that's going to give us the area under this curve. Okay, so where do we start? Let's go camera. So let's get rid of that. We've got 128x minus 32 is our function. Our domain is just going from 0 to 2, so what I'm going to do is I'm going to go to the window. Wow. I'm going to go from 0, x max 0 to x max 2, because that's our domain. If you remember anything about linear functions, the y-intercept is where it starts, and so it was negative 32 was the y-intercept. So I could go down a little bit further, but I think we're okay there. 128, so I'll go to 128, and 2 times 128. That's going to be like, maybe I better go to 300. So I'm just trying, my y max should be maybe 300. So I hit that, and there's what my graph looks like. So what I'm trying to do is get the area underneath the curve. So now notice this is actually going to be negative until here. And then I get positive values here. and then I'm going to get positive values. Okay, so this is those who are watching on the video. I don't think this is going to show up on the video, but those in the class, let me just actually draw the picture of what we're going to find here. Let's see, how can I do this? Actually, I think there's another way I can do this that will show on the video. Let me go. Let's see if I can do this. There we go. And how do I get this thing off the screen? I don't know how to get that off the screen, but at least this will record in the video now. So what we're trying to do is we use this left-hand side for the top of the rectangle, and we go to about 0.5. So we're going to get this rectangle here. We come to here, we go up to hit the function, we get that function value, and then we draw a rectangle to here. From 1, we're going to go up and get this function value here as the height, and then we're going to go over to about 1.5, and then from 1.5 we're going to go up till we hit the function, come over to 2, and we're going to find the area of these 4 rectangles, add them together, and that's going to be our estimate. It's going to be a number, right? Because it's area of 4 rectangles. What's the base of each of these rectangles? About 0.5. How did I get that? Well, we're going from 0 to 2, and we're doing 4 divisions. 2 divided by 4 is going to be 0.5. So each of the rectangles is 0.5. Now how do I find the height for each of these rectangles? Let me show you a tricky way to get that. Let me see if I can record this as a picture. I think I can. I apologize for those arrows in the way, but I'm not quite sure how to get rid of them. I'm going to go to the table set. I'm going to start with the table at 0. That's the x value. And I want my table to change by what? Not 1. You said it? 0.5. Good. And then I'm going to have it on auto, not on ask, just on auto. And then I go to my table and watch what it's going to give me. At 0, I go to negative 32. At, let's see, cheat a little bit here. At 0.5, I've got positive 32. At 1, I've got 96. At 1.5, I've got 160. So now what I'm going to do is I'm going to write those values here. So I've got 0, 0.5, 1, 1.5. Those are our x values. So I'm going to have negative 32 times what? Yes, 0.5. That's one rectangle. The next rectangle has a y value, the height of positive 32. So I take positive 32 times the base of 0.5. Then I've got 96. And that's, maybe I should put that as a dot instead of an x. Or that's not an x, so multiplying 96 times 0.5. And then the last one, 1.5, is 160 times 0.5. So you'll see that each of these is just tedious. You have to kind of draw the picture, figure out where your rectangles are, and then just get the y values for those.
What
And
about the two?
the 2, because we're doing the left boundary is always where we get the height. And then the right-hand side ends up at 2. If we were doing a right-hand Riemann sum, then we would have started at 0.5, did at 1, 1.5, and then at 2. So you use either the left boundary or the right. Okay. And so we just multiply and get all these numbers. 5 times 30, or 0.5 times 32 is what? Anyone got that one? Negative,
Or negative 16.
negative 32. Okay, that makes sense. Should have been able to do that one in my head. But again, sometimes you're thinking so much about the process. You know, heck, I even sometimes forget what 1 plus 1 is when you're doing it, right? So you use the calculator. So negative 16. Oops, getting messy here. And then we, where were we? 32 times 0.5, so that should be positive 16. So those kind of just knocked each other out, canceled each other out. How about 96 times 0.5? That's half of 96 is... oh, I didn't put the point, so 48, yeah. So 96 times 0.5 is just 48. And then 160 times 0.5, or divided by 2, it should be 80. Add all those together. Negative 16 plus 16, that's 0. 48 plus 80 should be 128. Did I get that right? And then you should put that in, and hopefully you get it right. Hey, you did. Yes.
So can you just find the derivative of the original equation and not have to avoid that? Because if you just looked at it and set it as an x and got rid of that, you can just get 128.
What you would be doing, there is a way to do this, and since we know this answer, I'll show you sort of the shut, but it won't give you the right answer because it'll be exact. In fact, actually, I told you that I was going to show you how the calculator does this. So, yes, there is a method for doing what you were talking about. Let me show you how you do it with the calculator. You go back to the graph, and there is a function under second calc. So if you can see. So I did second calc. There's this function 7, which is going to integrate for us. So you come down here, and I believe you have to enter two things. You have to enter the starting value, so the lower limit. The lower limit is 0. We hit enter. Then it asks for the upper limit, which is 2. Next value of 2. Watch what it's going to do for us. It actually draws very, very fine rectangles, fills it in, tells us that the actual value in there is 192. We came up with about 128 because we only did 4 rectangles. So if we were to do like an infinite number of rectangles, we'd come up with a 192. 192 is the exact answer. But what do you think if we put that into WebAssign? You're not going to like it. That's what. So they want you to go through this, but this is equivalent to when we were doing derivatives with limits. It was tedious. It was painful. So we only asked you to do about 4 of these, or 5. But yes, I agree with you. It's kind of it's not the best way to do it. Let's see what I want to do here. And then let me show you how we would do this with calculus. And I'm going, let me see, let me take a picture. Kind of going off memory here. I'm not sure if this is going to work or not, but hey, if it doesn't work, then I just look foolish, but hey, so what, right? I believe what we need to do here is this is the integral from 0 to 2 of this function. So we need to first find the integral of 128 x minus 32. And we want the limits to go from 0 to 2. So how would we integrate this? We would add 1 to the exponent and then divide by the new exponent. So x to the 1 is going to become x to the 2. 128 divided by 2, 64. This one is going to become minus 32. It's x to the 0, so we add 1 to that. That becomes x to the 1 power. And divide by 1, which is that. Then what we do is we're going to plug in 0 at the lower end, 2 at the upper end. And then we're going to subtract the difference. So we're going to take, let's see, how do we do this? It's been a while. So we plug in the 2, so that's going to be 64, 2 squared, minus 32 times 2. Minus the bottom end is the bottom limit 0, so we plug in 64, 0 squared, minus 32, 0 plugged in. So do you all agree that this whole bottom part, this back part here is all going to be 0? Good. So we got 64 times 2 squared, which is 2 squared is 4. 64 times 4 is 256. And then 32 times 2 is 64. If you take 256 minus 64, hopefully you get 192, which is what the calculator gave us. So that's really what this is supposed to build you towards, and I think we will do that in the next section. We will actually, yes, it is much easier than this tedious stuff. And I said, well, why did we have to do all that? Oh, you just have to do it because the teacher said so. But it's the basis of everything that was built on it. And this is a little abstract. It took them years to get to prove that this was the same. But they were taking these little Riemann sums. But that's all they had to do. All they could do was draw graphs, draw a bunch of rectangles, add them all up by hand, and that was mathematics, 200 years ago. Yes.
So you don't include the last function when you add them?
We do. What do you mean?
Oh no, I'm talking about when you do the x and y table.
Oh. Yeah, if we're doing the left hand, you start at the left and you don't use the last one. Yeah, we didn't finish. Well, we finished with 1.5. If we were doing a right hand sum, then we would have started at 0.5 and we would have ended at 2. Okay. So far so good. Is that?
Wait, can you repeat that last part? If you go from the other side.
So if you're doing a left hand sum, you start at the left. And then, yes, you will not use the last limit. If you do a right-hand sum, you start over 1, and so you'll end up using the right-hand limit. But you never use both the left and the right. You use one or the other. So you're right. There's error right from the start. And the only way you can get that error down is to make smaller and smaller rectangles, which means more and more calculations. But again, if that's all you got to do, that's all you have. But we got calculators that'll just go to second calc and we'll get it. So when we get to the next section, you'll see we can either do it by hand or that we can graph it and use that little function, the built-in one in the calculator to actually get it. Okay. Again, that's why I like having the, and what I'll do is I'll work on getting that program, so if you're here Thursday, I can download it to you. So if you want to wait on this and say, I'll just wait till the program arrives, that's fine. Because it's really cool. It draws the rectangles for you, it gives you the exact answer, you plug it in and you're done. The one I've got is called Curvature. And where I got it, and this is a good resource for anybody, for TI calculators, is you go to this, the website is ti-calc.org. It's a nonprofit that collects programs for TI calculator. They have a huge database of programs that does basically everything. And like if you're taking chemistry, they've got chemistry programs and stuff. You download them, but then the other thing you need is you need to go to ti.com to download their TI Connect, which allows you to connect your computer to the calculator. And I did that with the Mac version, and it wasn't finding my calculator. It might be my cable, it might, but I know when I do it with the Windows programs, it's a lot easier. But then you're able to find a program that does something, download it to your calculator, test it out, and like I said, it's really cool. Okay. So this is another one. Again, it's a length of 2. It's going from -1 to 1, so it's 2. Each of the intervals will be a half because that's 2 divided by 4, and we just have a different function. Okay. You okay with that one? Here's an x squared, so that's going to be quadratic from -2 to 2. So how wide is this one? -2 to 2. 4. We're doing 4 rectangles, so how wide is each of our bases?
1.
Multiplying by 1 is a lot easier than multiplying by a half. So this one's not going to be too bad. Okay, so let's look at this one so that we could focus maybe more on the process than on the arithmetic. Okay, so what we need to do is for this one, we need to graph this function, y equals this. We're going to go from -2 to +2. We're going to use 4 rectangles. So the first one will be at -2. We're doing a left hand. -2, -1, 0, and +1. Okay. Let's bring up our. There we go. So. And it's 33 x squared, which again is going to be a quadratic, so it's going to go up. And this time in my window, I want to start the x minimum at -2, going to +2. The function's 33x squared, so it'll start at 0 and all the values will be positive. I think I'm just going to start at 0, and let's what's 4 times 33? 120 something. Maybe if I go up 132, we'll just, you could go to about 150, you'd be fine. Okay, so we see this, and again, what we're looking to do, we're physically going to do, is we're starting with the left side, so we're going to go from here to the top of the graph. That's the left corner, and then since we only need 4, we go till we get to -1. So there's one rectangle. From -1 we go to this part of the graph, so that's the y value, and that gives us this rectangle. From 0, oh, we're right here, so that's a real slim rectangle. And then from 1, we go to the top of the graph, hit it, and that gives us this rectangle. So we're going to add 1, 2, 3, 4 rectangles together. One of them is a very flat rectangle, it's going to be 0. And what we're going to do is we're going to pull these y values. The x values, or the bases, are all 1, 1, 1, 1. Get the areas, add them together, and that gives us our estimate. Again, you can see it's not a very good estimate, is it? Lousy estimate, but this is, again, all we had to do. The only way we could make it better is maybe to do 8 rectangles, but then that's very tedious. Okay, so we've got this going on. Let's take a picture of that. And then let's go to our table set. I want my table to start where? Where's the left boundary? -2, good. And since I'm going from -2 to 2 and I want 4 rectangles, what should be my interval? 1. So it's the width is 1. Okay. So that's how I'm getting those. I hit table, and I'll get all my values here. So at -2, I've got a height of 132. So I'll show my work over here. -2, so it's got the first rectangle is going to have a height of 132 times a base, or a width, of 1. The second rectangle starts at -1. It'll have a height of 33 times 1. The third one will have a height of 0 and a base of 1. And the fourth one, starting at 1, will have a height of 33 times 1. And again, notice we did not use the 2 because we're done. We've got all the rectangles starting from the left. Okay, and again, our math is a lot easier this time. Multiplying by 1, 132, 33, 0, and 33. Add those all together. It's 5, that's 198. Thank you. And that's good. And again, when you do it, they'll probably have a different number in front. 198. Submit the answer. Good, 2 for 2. Players manufacture the random sum of n equal 5 to estimate the cost of producing the first 5. Okay. So again, I'll kind of help you. So if we're gonna produce the first 5, we're gonna go from 0, 1, 2, 3, 4, 5. guess we'll try this one because they don't say whether they want a left bound or a right or a central bound. My guess is that they want, when they say just a Riemann sum, since they haven't said a left fund, what they want is they want us to use the middle value. So the middle of our rectangle is halfway, the height of a rectangle is halfway through there. Does that make sense? So instead of, so halfway between 0 and 1 is 0.5. We'll use that value for a height. Halfway between 1 and 2 is 1.5. Between 2 and 3 is 2.5. 3 to 4 is 3.5. How many do we have so far? 1, 2, 3, 4. The last one is 4, halfway between 4 and 5 is 4.5. I'll put it down here. Again, what is the width of each of these rectangles, the base? Zero to 1. They're all going to have a base of 1. So what I need to do is put this function in my calculator, find the y values at 0.5, 1.5, 2.5, 3.5, 4.5. Those will be the height of the rectangles with measured from the middle of the rectangle. Multiply each of those by 1, that gives me an area, and then add them together. Okay, so a little bit, we'll try it maybe in a little bit more abstract form. So we'll do 28 minus 7x divided by 1,000. Okay. And again, we could, so we're going to go from 0 to 5. See what that looks like. It's a pretty flat function. Our table, we want to start at 0.5 this time, and we want it to change by ones. Okay. The table. Wow, not much difference. Did I get that in correctly? I did, didn't I? 7x divided by 1,000. I guess that's... Okay. So, again, what we're going to do...
I mean, y is going to stay the same, right?
Pretty much, yeah, it's 27.997. I guess if you round those, that looks like a bunch of 28s. You think we'd get by if we round that to 28? See, what does the question say? How
It's just to answer to the nearest cent.
to the nearest cent, which is 0.02. I don't think we'll get close enough. 0, because 2 decimal places, it will probably throw us off. So what we'll do is, so the first one is 27.997, and then it's 27.99, and then for 2.5 it's 27.983. Notice since I have to round to 2 decimal places, I go to 3 when I do my sum, so I have something to round. Where are we? We're at 3.5 is 27.976. 4.5 is 27.969. Has anyone added those together yet? No? Anyone want to? Get some free cake in the fridge if
So we're leaving 4.5 out.
I think I did 4.5, didn't I? Let's see, 1, 2, 3, 4, 5. So you should get 4.5 as well. And I might have, hopefully I got them all. Let's hope. I come up with 139.915, so I would round it to 92. Does that seem reasonable? So leave all this stuff up here. So 139.92. And I have no clue whether this is going to get marked right or wrong. One of the things I'm concerned about, it didn't say left or right. Hey, it worked. Okay. Anyone else kind of tired of these? Okay. How many did we do together? We did 3 of them, didn't we? So how about if you do 3 of these, we'll call it good. If you want to get some extra credit, you can do the other ones. But when I score these, I'll change the point value to 3. Anything above that gets you extra credit. Because, like you said, isn't there an easier way? What are we really going to use this for? Is get the concept down that what we're getting when we get an integral is the area under the curve. We're using but it's very crude. It's a very crude way to do it. What we'll do on Thursdays, we'll come back and we'll look at the more elegant way of getting the exact value using the integral. So we're going to put the 2 things together. But for this lesson, these 3 we did is fine. Again, I'll let you use any of the 3. But as long as your homework has 3 of them done, you got full points. Okay, the full 20 points. If you get the other 2 done, because there's only 5, get you another. That's a lot of points. But anyway, get you another 15 points of extra credit. I think something like that, 12.5, whatever. Yes.
What's like all the assignments due by? Is it
As long as you have things, what I'm going to do, the 7/19 is our last official day of class. By that time, I will be in Thailand, so actually I'll be a day ahead of you all, but that doesn't matter. As long as you have everything by 7:50. What I'm hoping is a lot of you get it done earlier, which is fine, or later, but you have till 7:19. If you need till 7:20, it's not real crucial, but hopefully you get it done. And what I do is each week I pull up what's in the homework. I have WebAssign send me an Excel. So even if you miss something like on the last update, if you get it done between now and next weekend, the next update it'll get picked up and it'll update. So, and I think I've got zeros in on some, but that's just because this is where we should be, but zeros will get replaced with full credit at any time. So you have that time to get all the homework done. Now the thing about the test is you should have done the homework because that's what the tests are about. But I've got students who will take the practice test and they'll study that and they'll do well. They'll do well on the test and then they go back and do the homework. Who am I to say that that's a poor way to do it? It works for some students, so that's fine. If you want to get the homework done first and then go through the practice test and take the test, that's fine. But what we're going to work on is actually by the end of this week, I've got to get busy on writing some tests though. We'll have 11 and 12 open, that you can take that basically anytime you want. After this week, we'll have the content covered. I'll have the test for 13 and 14 ready to go by the end of the weekend. So then next week, if you wanted to bust everything out and take the test and you do fine, you could be done because you won't need to take the final if you do well on these 3 tests. And again, I'm opening up a little bit. If you're like, I got students who I'd be happy with a C. So you got 70% averages. You got you got enough for a C. If you're happy with that, that's fine. But if you want an A, you could also, you'd have enough points to get those A with just the 3 tests and the homework. Homework is about, I think I got it to like 400 points, 480, somewhere in there. And again, if you do the extra credit, you could that could help a lot. That gets you about 400. The tests are roughly about 600 points total. So I'm going to up the values, and again, once you got 900, 900 or above, you got an A. And then with the final one, I'm going to use that for as a second test to retest if you didn't like how you did the first one. And they'll be very simple. They'll be the same. I guess 14 questions for the first one. I'll just change the functions, but they'll be the same question types. So you can study from the same study sheets, and you'll be fine. And the final is, just think about, is really 3 individual retests. But if you do good the first time, you don't have to worry about retesting. Does that all make sense? It got so hard on my helmet was so hard on my head today, I think I fried part of my brain. So nothing makes sense once I say it. But never had to get that hot. But okay. 3 problems in your full, and then go back and do the ones from 13.1. We'll finish up the course content Thursday, and be ready to start our careers, right?